All right, hello. So we're going to go over the USRP RIO getting started, looking into the streaming project today, and hopefully that'll help you understand where you can edit parts of the project so that you can, modify it for your own applications. So USRP RIO getting started projects, understanding use and modification. So my name is Jordan Yamada from Application Engineering. All right. So just to preface this, this training will walk through the NI-USRP RIO Getting Started project and help you gain a better understanding in order to make modifications for your specific use cases. The training is meant to build on top of LabVIEW and LabVIEW FPGA as well as high-level USRP knowledge. So we're not going to get into. Hopefully, we understand the platform of LabVIEW and LabVIEW FPGA, but yeah, if you need to go and find those resources, definitely, you know, there's definitely a lot of resources on that. So, but that's not what this training is about. And if it isn't the case, then we still can find benefit in this training, but the best value will be to have some prerequisite knowledge. So just a quick outline. We're going to go through the overview of the project, then through the data path, and then through the synchronization and triggering path. So yeah, there's kind of usually two main things that you need to do is, you need to send data, and then when does that data be sent, and, how are you going to send that data? So we'll look at that. So first, if you open up LabVIEW and you go to create project, you'll get a window like this. If you have NI-USRP installed correctly, you will have this option, and then you can go to NI-USRP multi-device synchronized simple streaming. So actually, a lot of the applications that NI does build uses this project as a starter place. So for your applications, that should also be a pretty good start. Although you can look at these other projects as well. Overview. So this sample project contains two host VIs that run on the host computer, and then two FPGA VIs that run on the FPGA. Each host configures the device input and output ports and configures a data stream between the host VI and the USRP RIO. So what this really means is that let's maybe take a look at the project here. So if I open up the project, this is kind of what it looks like. So it has two hosts, an RX and a TX streaming host, and then it has two FPGA bit files or two FPGA VIs. So streaming Xceiver or transceiver sync PPS trig, and then streaming Xceiver sync AUX. So we'll get into kind of what those two things mean later, but that's what it's talking about in this overview. So here, the sample project performs the following tasks. So streaming data from the host to the device, and then streaming data from the device to the host. So that's generally how it looks like. It also talks about where to find how those streams are implemented. So if we look at here, we can see that we have the RX0, RX1, RX2, RX3 hosts, host FIFO implemented, and then the TX0 and TX1. So and then secondly, there's two ways we kind of like to move data around between the host and the USRP or the FPGA. So we either move it in a continuous stream, or we have these finite streams. So either the host, we run the host and we just assume that we're going to get a stream of data, and if it doesn't have enough data to be read, the FPGA reports a buffer underflow. So this is like we're just assuming that the FPGA is always sending up data, and we're expecting this data, and we'll process it that way. So really, there's like not as much of a handshake, if that makes sense. In finite, the host periodically sends a block of samples to the FPGA, and then we specify the size of each block and the number of samples host VI and the front panel control, and then a block of data is read on the FPGA when the start trigger is asserted. So this is kind of like the host is more a part of it, meaning that the host will then tell the FPGA how much samples it expects to send. It'll send that amount of samples, and then when this start trigger is asserted, then we'll start. So yeah, so that's part of the synchronization path that we'll talk about later. But this is again the overview of kind of what this project does, so we have a good idea. And then you set mode using the generation mode and the host VI front panel control. So we'll look at that later. And then this is similar. So this one was talking about continuous and finite in terms of writing data. And then this is continuous and finite in terms of reading data. So it's just basically, are we sending data to the FPGA or the USRP, or are we getting data from the FPGA and USRP? And it's the same idea. Either we're going to just assume that one side is just continuously sending data and we'll expect that data, or we're going to wait for like a handshake where we're going to request some samples from one side or the other. So yeah, so acquisition mode is the way you do it on the RX side. So this DMA FIFO. So if you've taken some FPGA classes, you should know what this is. But generally, a quick overview is, let's say that this is my USRP, and then I have my MIXI connection and whatnot, and then we have the LabVIEW host here. So we're going to put some data into this thing called the FIFO method node. So if you ever see something like this, that means that the data that goes into that block is going to be moved through some mechanical means, or I guess not mechanical, but there's some hardware involved that kind of sets this up. So this goes into here, goes into a buffer, then goes into the DMA engine, then goes onto a host buffer, and then it comes out through an invoke method on the host. So what it would be is, say we have the FPGA and it's acquiring some kind of RF signal. So we get a bunch of IQ samples, we throw it into this method node, and then we're going to start filling up this buffer. So we'll start filling up this buffer, and then when we have enough data, the DMA engine will then copy that data over to a host buffer, right? Because we have the FPGA here and then the host here, or like your Windows system or maybe your RT system, and then that will copy the data. And every time you call this method, all that does is it takes these samples here, moves it to here, and then moves it out. So here it's just just trickling one until it fills up, and then here it's just going to grab a chunk like 4 elements. So we're going to grab 4 elements and then move them up, and then you'll have them existing in LabVIEW memory. So hopefully that makes sense, and then we're going to make use of this knowledge in dissecting how the data path works. So we get into the 2 host VIs, the 2 different hosts that I talked about earlier. Where there's a RX streaming one and a TX streaming one, so that's generally that. By the way, all this information is copied out of the project. So the project has this NI-USRP streaming sync.html. So you just double click that. That will open up a nice HTML file for you, and you can just go ahead and read it there. At least in this video, you can pause the video and kind of read what's going on. But generally, it's just saying that we have 2 VIs. One is going to be the host, and one is going to be the RX, and one is going to be the TX. And then it's talking about how the trigger lines are configured. We can talk more about that in the synchronization portion of the overview, but I can read this real quick. But the PPS trigger lines are used to send synchronization triggers between the USRP devices. The synchronization trigger is not a PPS. A true PPS, for example, is an internally generated PPS from the CDA. So that's a clock distribution module, the 2990. Cannot be used to send synchronization triggers required by the USRP devices. So all this is saying is that the USRPs, they do technically have a PPS in and a PPS out, but they're not a true PPS because I think the threshold is a little bit lower than you would expect. So when you are using multi-devices, it's saying that you probably want to use a device like the clock distribution module to kind of forward those pulses. So that's all that's saying. So usually you'll use an octo clock or something like this clock distribution module to synchronize them. But we don't have to talk about that in specifics. We can just talk about the high level synchronization scheme, and then you can make a decision of whether of what kind of device you want to use to implement that. The FPGA VIs, there's two. There's one that's the aux FPGA VI, and then there's one that's a PPS one. The only difference between these ones is one reads a trigger from the PPS line, and then one reads a trigger from the auxiliary line. So on a USRP, the auxiliary port is, I think there's a DB9 connector or DB9-like connector on the front of USRPs, or at least the USRP RIO. So that's the one that you're gonna, if the trigger is coming in through that line, you want to use this VI. And then if the trigger is coming in through the PPS trigger line, you want to use this VI. So that's the general difference there. Yeah, so PBS trig, previous trig out versus the aux IO connector. So it's just a matter of hardware. But, the FPGA is defining the hardware logic, right? So depending on where that signal is coming in, you want to use these different files. So running the sample project. So, we'll kind of go through this, but, just ensure all your hardware set up. Make sure you know what your USRP RIO resources are called. So you need to, make sure that when you're running the project or you're running the VI, it's pointed to the correct USRPs that you want it to run to. So that's a start. Wire and configure all your devices using the same reference clock. So everything does have to share a reference clock in order for this thing to work. So just know that. If synchronizing, so if you have, a couple USRPs that need to all TX or RX at the same time, then you'll need to, follow this kind of synchronization scheme. So basically, it will be the first USRP will send a trigger out, and then the clock distribution module will distribute that first trigger out to all the rest of the USRPs, and then when it gets all that signals, when it gets that signal that it routes from the first USRP, then all the USRPs will start, doing whatever activity they need to. So basically, it's like one starts it, and then there's a chain reaction that hits all the USRPs, so they all start at the same time. And then, if using a clock distribution module, you must complete the following tasks. So set the primary ref to external, and then wire a reference clock to the module. So so basically all it's saying is if you're using the specific module, this is how you configure it. In the project window, open the host VI. So open up one of these host VIs, update the RIO devices, and then click run, and then you should get some generated data. Click stop, and then experiment with different values in the front panels, and click run if you want to update things on the fly. So you must restart the VI for new settings to take effect. So that's something that you should know about. That the settings are done initially, and then once they're set, until you restart the run, they'll be the same. So data path. So let's understand how data moves from the host down to the FPGA and back to the host. So the first of all, we got, this is the general block diagram of what's kind of happening. So you have this, front panel UI that then, configures how we generate samples. Then we send those samples down, and then it hits a host buffer. Then we have the FPGA buffer, right? Remember, like in the in here, we have the host buffer and then the FPGA buffer. So that's the same thing, host buffer, FPGA buffer, and then we hit the RF. The RF does, its thing, and if we're receiving some samples, the RF will get some samples, and you basically follow the exact same path back. Except, you don't have to generate samples, you just, read them or analyze them. So, same idea. So let's look at what that looks like in the code. So front panel UI, what that looks like is this. So this is the front panel of the example project. So, when we read of how to run this project, you got to make sure you set up your USRP resources correctly. Then you got to set up your frequency reference source, and then select which type of synchronization you want. Yeah, and then so in figuring out how to generate how many samples, you need to tell it, how many samples you want to generate. What is that tone frequency? So by default, it's just going to generate some sine waves or tones, and that's what's going to come out of the RF. Of course, you can edit, that IQ data and make it something else, but uh, for the sample project, we're just going to start off with just generating a tone, right? And then so if you double click, TX configuration, you'll actually see on the block diagram, this is what will come up. So just all of this data ends up in here in this cluster. And then if you want to learn more, like you'll see a lot of clusters kind of going around. So it can be harder to track down data because it's all kind of in this cluster or in this type def. You can go to help, show context help, and then just hover over, some of the things, and you can see kind of what the TX config is doing. So it sets the configuration values for the TX signal chain. Yeah, so that is something that you can use, and I would definitely, if I was looking through the project, use the context help to help me figure out what is kind of going on inside of these clusters. Great. So now we know, how we're kind of configuring things. Let's look at how we generate samples. So back to the block diagram. So we tell it, give it these numbers, give it, all this stuff, and then this is the first, VI that we hit. So we look into there, and then we double click it again, and we have some more stuff. So we look into there. And then we get to, some of the meat and potatoes of what is going on here. So from here, it's a little harder to figure out, where exactly we're generating samples. But if you notice, it says I and Q here. It says TX channels. So most likely, this is our data that's being generated. So that's why this training exists, because it's maybe not as obvious, but if you're pretty proficient with LabVIEW, you can kind of follow these things through. So let's follow down into this block to see what is generating that I and Q. So we click into this block, we get this block diagram, and then we can follow I and Q here, follow it into this block. And basically you can see that, that sample rate and number of samples that we saw all the way back in the front panel, so number of samples, tone frequency, sample rate, that makes its way, that makes its way all the way down into here, so that, does, channel down into this little smaller VI here. And then we use this VI here, that's just generate sine wave. We go to an amplitude, tone frequency, stuff like that, and voila, you have your I and Q values. Notice it's also scaled by integers. So you do have to give the USRP, you can't give it doubles for I and Q values. You need to give it like an actual I16. Great, so that's how we generate the samples. Now let's see how we actually send those samples down to the FPGA. So let's go to send samples. So we can follow this. See, this is TX channels. So we can follow this down over here. And so we can look in here, and this is what initiate and generate multi.vi does. It writes baseband waveform to the device and then initiates generation. So the thing that writes baseband waveforms is probably the thing that's going to send the samples. So let's go look into here and look into here. Let's see. Look, we have I and Q here. So we can follow TX channels. So they're packaged, right, in that previous VI that we looked at. And now they're being unpackaged and then dropped into here. So we can double click here. And I and Q. So it looks like I is the lower bits and Q is the higher bits. So it looks like we do some bit packing That's something that you would probably learn from the FPGA classes and your FPGA knowledge. So we'll bit pack them. So, those samples can, exist together in a I32. Um, so we don't, we don't lose the coherency of the I and Qs next to each other. And then we can click into here, go into the data, and looks like, this is a very familiar block, right? This is the DMA FIFO, right? So basically, depending on the data and depending on, which, port we want to write to, we're going to call different DMA FIFO writes. And basically, this will queue up the data in the host, and then the DMA engine will then move that data over to the FPGA when it's ready to. So yeah, so that's that. So that's how we send samples. So you can see how, we have some numbers and we generate the samples from that. Then we send the samples and then we have them on our host buffer now. But yeah, so one thing that, was interesting is, from here, it isn't really, there's nothing that tells us how big or small the host buffer is. So let's see how we configure our host buffer. And it's actually not in code. So if we look into here, look into here, look into here, and then look into here, we can actually see that on the FPGA, we actually configure a depth of our host FIFO because depending on the number of samples that we want from txconfig, that'll actually affect how big we should make the host samples, right? If we're sending, large amounts of data to the FPGA, the host needs to be able to keep up with that, and the way that it can keep up is that it has a larger buffer. So the FPGAs can get the data at the rate that they're expecting it. So basically here, see, we can look at number of samples, and then from here, we tell it, this is the amount of samples we want to generate. So that's going to tell the FPGA some, what samples we can generate. And then we look at the host FIFO depth. And basically that is kind of, we get the number of samples multiplied by that by 8, because I think it's in bytes. So we're just making it 8 times larger. And then whatever is bigger, we will go into here and then ask LabVIEW to make a buffer that's that big. And then, basically as the depth comes out, if it's, not as big as we asked for, we're going to say, hey, we don't have enough memory on this computer to generate the host FIFO as big as you want it. So just wanted to let you know that. So we're either going to generate an error, or if we're all good, then we'll generate no error and we'll, go off. So yeah, so that's how we configure the host buffer. So we have some, some programming that kind of sets that up. All right, so the FPGA buffer now. The FPGA buffer, so I think I did a misnomer earlier that the host buffer wasn't done by programming. But yeah, but the host buffer is set up programmatically. The FPGA buffer is not. So let's look at how that is set up. So remember earlier in the the lesson, we kind of looked at, this is where we set up those host FIFOs, right? Because they're actually using hardware, so we need to configure them. So yeah, this is where they live. And so if you double click one of these, you'll actually end up in this host FIFO properties. And here you can tell it how many elements you want it to store for you. So since the FPGA, is hardware, you're writing hardware basically, right? You need to tell it, hey, I want you to make this much space on the FPGA for me. And that's, it's going to try to do its best. As you can see, if you put, 1032 or 1023 here, it's actually going to generate 1029 because I think it has to be in specific increments. It's kind of like, like RAM, where you can only have it in sizes of 8. Or memory in general, you need it in sizes of 8 because everything's a binary system. But anyways, that's what we're doing here. So that's how you would ask it for a larger or smaller FPGA buffer. The implications of this is basically, If your host is going to send a lot of data down to the FPGA, then maybe you want a bigger, number of elements, right? Like, I think if you want more bandwidth, you definitely need, a bigger host, or a bigger, well, I think you'll need a bigger host FIFO, and you might need a little bit of a bigger FPGA FIFO as well. I know some of the USRPs do have, some larger bandwidths, right? So if you are going to make use of that, you also have to think about your transfer mechanisms, because yeah, definitely the USRP can do that, but you also need to get that amount of samples down to the USRP or back from the USRP in a reasonable manner, and buffers are going to be the best way to do that. And then if we look here, we have our FPGA buffer. So this is just kind of showing you what the FPGA code looks like. So we're just kind of scrolling through. So that's kind of what that looks like. And then if we look into, this is top level code. So we'll zoom in a little bit into the streaming transceiver engine. You can double click this, double click this, double click this, and this is where the data is coming out. So you notice it's coming out one at a time, and it's in a U32, right? So so this is your FIFO 0, your FIFO 1, so for antenna 0 and antenna 1, and this is your data that's coming out. So this is where the IQ data, like, so for example, if you wanted to do some processing, well, probably on the TX side it doesn't make sense, but on the RX side, if you're doing some processing, and you want to do it on the FPGA, this is kind of where you would touch it, right before you send it up to the FIFOs. So, yeah. And then let's look at how the data gets to the RF. So, same thing. We look in the FPGA code here, click in here, click in here. And so we got data out of here, we're sending an array of data down to here, and then we have this digital up converter. We can look into the digital up converter. And it looks like we do a couple of DSP things to get it to match the sample rate that we requested. Input sample rate, gain, delay, frequency shift, phase, impairments. So, basically, you don't have to worry about that. The project is doing it for you. You have the data here. It turns it, and shifts it and does whatever it needs to, and then you get the I and Q out here. And then, looking back here, I and Q, then, so you notice that, you then unbundle in the array, and then you have RF0, TX1I, RF1, RF0, TXI, RF1, TXI, RF0, TXQ, and RF1, TXQ. So this is how the data is getting, and then in this block is basically, once an IQ sample gets sent to here, that's what the hardware will generate. And it'll generate it based on how fast this is going. So this is going at the data clock. So yeah, so that's data all the way from the host all the way down to the FPGA. So yeah, so something that will be, this is more for if we're being more interactive here, but if you want, you can try to open up the project and follow the data for yourself on the RX path, because we just went through the TX path. And then we can look at the answers in the following slides. I'll go through them pretty fast, but you can kind of run this exercise on your own to just check your understanding. So yeah, so the front panel UI, it's going to be the same thing, right? There's one UI for everything. Sample analysis, so we have these tabs here, and then the sample analysis is kind of coming here. So if you open up, so this is the other project, right? There's the TX project and the RX project. It's the RX project. So this basically, you'll kind of get the samples here, and then we do some stuff on the host to get a power spectrum, some power levels, and then just show the raw IQ data. And then sending samples will look like this. So if you click into all the VIs, and you eventually get to something like here, that's what that looks like. The host buffer. So we kind of set the host buffer the same way, it's just on the other side. And then the FPGA buffer, same thing. And then for the RF, we're going to look for these guys. So it's also in that streaming Xever engine. It's just going to be in a different VI. So just that's where you'll find that. And then the RF, it's basically the opposite path, right? So this is coming in from the hardware. We're going to do some stuff to it, digital down converter, then put it up to the FIFOs to get it to the host. Great. So that was pretty quick, but from that, you should have a better idea of, where in the entire chain do you want to modify IQ data, moving, all the way from the RF path to the host, or from the host down to the RF. So now let's understand kind of synchronization and triggering, because, for right now, we don't know when these samples are being sent out or anything. So let's look at the synchronization triggering. So for our purposes, let's characterize synchronization really quickly, because I think that can mean, a bunch of different things too, depending on what your application is. But for our purposes, we can characterize synchronization in two aspects. The first one is starting at the same time, and then the second one is not drifting apart. So if you're running a race and you want the two people to start at the same time, usually you have a trigger, right? You shoot the trigger, and then as long as they run at the same rate, they should finish at the same time, right? So in order to implement synchronization using, in signal-based synchronization, similar to the analogy of the runners, we're going to have a pulses per second, right? And this enables us to start at the same time, because everything that we do, we're going to wait for a trigger, and then a reference clock that allows us not to drift apart. So this is just ensuring that, I guess in the analogy, that the runners are running at the same pace. So yeah. So what is triggering? We can think of triggering. As choosing, when we want the samples, when we want to take the samples, and when we are synchronized. So basically, if you look in the project, you'll have all these options for triggering. So as I said, you want to start at the same time, but what is the thing that you're going to use to figure out that you're starting at the same time? So either we can have the PC send a trigger to the FPGA. We can have a digital edge. We can have an RX start trigger. So basically, when we tell the RX to start, we can send that trigger out. When the TX starts, we can send that trigger out. We can send it as immediately as the FPGA is ready, or we can have a trigger based on the future time event. So there's a lot of different ways we can do the triggering. So it all depends on your application, right? Because I don't know, or you have to figure out when you want your RX and TX to start. So this is this is the functional block diagram for sync and triggering. So again, we're going to start from the front panel UI. We're going to send some settings to the FPGA. We're going to receive some settings from the host on the FPGA side, and then we're going to wait for trigger, and then we're going to send samples, and then either we're going to come back and wait for a trigger again, or if it's continuous, we're not going to wait for anything. We're just going to keep sending the samples, assuming that the everything is ready for us on the other side, right? Because in the continuous one, we're not waiting. In the finite one, we have to wait for a handshake from the PC. So, and then the same thing for the RX side. It's just kind of, it's kind of the same thing, because we're setting some settings, and then instead of sending samples, we're just going to capture samples. So the triggering is actually the same idea. Great, so let's look at the front panel UI. So, we have the reference frequency source, and then the FPGA I/O for synchronization. So this FPGA I/O, you can either remember those 2-bit files that we talked about. You can either have it as a PPS trigger, or you can have it come in through the auxiliary line. So that's what that is. The reference frequency source. So either you can have an internal reference, or you can ask it to reference from a clock. So if you're using one USRP and it doesn't care about anything else, internal reference probably works the best, because you don't actually have a another reference source. But if you're using a couple of USRPs, you're going to want to use either, like a clock distribution device or something like that to distribute a clock between all the USRPs and tell the USRPs to look at that reference source. And you would do that using this control. Now, the start trigger is something that we talked about. Currently by default, I think it's set to immediate. So whenever the FPGA is ready, it'll just send the trigger out. But sometimes we can set it to something else, like we saw previously here. So we can set it to any of these things too. And all of these controls, you can see them here, right? Reference frequency source, which bit file, and then txconfig. So now let's send the settings to the FPGA. So we can follow these three guys, follow them into, double click this VI and follow them into here, follow them into this VI. Let's follow each setting individually, starting with txconfig first and then which bit file is last. So txconfig, follow this, it goes into here, and then it goes into here, so start trigger, goes into here, and then it looks like here we set up a TX trigger select. So notice since we are setting the TX trigger, it doesn't make sense to use TX start trigger and to fix that we insert an error if that case occurs. So what that means is if you're going to ask the program to say, oh, let's send the trigger whenever the TX starts. Well, if you tell it to wait for the TX start trigger, then it'll never come because you're both waiting on the TX start trigger, and then you're in the TX mode, so it's never going to come because it's waiting for something that it's trying to do itself, if that makes sense. So so if you're in the RX mode, then that makes more sense, and this will actually change in the RX mode. So just that's something to note. It's good application practice to not let users do something that will put your program into a state that it shouldn't be in. So next we'll follow rich frequency source. So we'll go into here, reference frequency source, go into here, which so this basically is just an initialize USRP one. So you just have to tell the USRP which frequency source it has to look at. We can't go into this VI because it's kind of like a driver VI, so you shouldn't really be touching stuff in there. So just assume that when you give it that reference frequency source, it'll set that up for you. And then for which bit file, you go into here, you go into here. And so notice that basically depending on which bit file you select, it'll actually open up a different FPGA bit file. So it's gonna, kind of build up a string here, and then based on that string, it's gonna generate a path, and then it's gonna try to use that to open up the bit file. So remember we said we had two bit files, the AUX one, the aux one, and the PPS one. This is what this is doing. So basically all this is doing is selecting if we're using the aux bit file or we're using the PPS bit file, because that's why this is a string. So yeah. And then we can see we have the different bit files here. So these are the ones that this accounts for. But if you make a new bit file with your own modifications, you'll definitely have to modify this logic a little bit, right? But for now, all it does is it's either going to select the one at 120 megahertz or the one at 200 megahertz, and then it's either going to be PPS or aux. So yeah. Great. So now that we set up the FPGA to say what trigger we're going to wait for, what reference we're going to use, I think we're ready to receive these settings and kind of implement that on the FPGA. And remember, all the triggering has to happen on the FPGA because it's all hardware based, right? We can definitely tell the FPGA that you can just start triggering like the PC trigger, but that's where kind of the synchronization and triggering is going to happen because it's all real time, right? So basically, the trigger select that we did earlier, that's going to write into here, into the TX parameters. So that's basically receiving the trigger settings from the host. And the PPS versus aux, that's going to just be chosen via whichever bit file you choose, right? And then the reference source, that's through the USRP initialization VI. So that's already set for you. So really, this is the only thing that's coming down from the host to the FPGA through that IO node, and then the parameters is going to capture that. So now for wait for trigger, we have this parameter that's captured, and then TX parameter comes in here. It goes into this block, and we can follow TX trigger select and then go into this block. TX trigger select, then go into this block. So basically, go into this block and go into this block. So you see, basically, depending on what is the trigger that we select, we kind of multiplex through these inputs, right? And the inputs are basically software trigger. This is the aux IO trigger. Other start trigger, event occurred, so that's like the future time event one, trigger enable, and then stream enable. So depending on all these guys, we're gonna set these guys up, and then depending on that, we're gonna then output this pulse here, and then when this start trigger is good, then it's gonna come out through here, and then we're gonna also, so basically this is just saying what trigger are we selecting. So if there's ones that are not the PPS, it'll come through here, and then the TX start trigger will go. If it is the PPS one, it'll just say, okay, well, you're going to use the PPS one, so we can wait for this trigger as well. And the PPS one will come down through here and then also start the trigger. So between trigger sources and TX start trigger, the logic will align when we want to start with PPS. So basically, what that means is, everyone gets the same PPS trigger, right? Because we're distributing that. But if it's, we have a trigger like the future time event or one that's coming from the host, it's going to be like, okay, we got the one from the host, and also, right, and we got a PPS start trigger, then we go to the TX start trigger. So basically, the PPS is just making sure all the triggers are aligned, because the host, when it sends the configurations down to the FPGA, that's not guaranteed to happen at the same time, and tell all the USRPs at the same time to wait. So it's going to say, okay, well, I'm going to wait for this trigger, but also I got to wait for the PPS trigger as well. So it just helps align everything. And then we send samples. So this green wire comes out of here on the TX status side. TX start trigger comes through here. TX start trigger goes through here, and then basically that is passed through. And the reason why it's not just like a gate, like a on or off, is because all of this logic has to hold back the samples accordingly before this TX trigger starts. So that's kind of why it's kind of fed through all these blocks here, logic-wise. The TX start trigger will trigger and allow the IQ data to flow through the RF. So yeah, it's flowing through the TX start trigger, but also there's other things like stream enable and TX reset and other things that are also gating these things that are more just kind of logistical stuff rather than just your application. So those are also there too. So same thing with the RX or with the data path. You can try to follow this yourself, and then the answers are shown in the following slides. So on the RX side, it's done the same way. Here we have the RX trigger select, and then we have the initialize USRP, and then this one is which bit file, which chooses the auxiliary versus PPS trigger, and then receive settings from the host. You're going to get the RX trigger select here, waiting for trigger, Same thing, it's going to be this RX trigger. So the TX trigger select was here, RX trigger select is here, and then capture samples. It's going to go, we're capturing some samples, we're digital down converting, and then doing all this stuff, but it's all gated by this RX start trigger. So you can kind of see that, and then that trigger is fed through here. So hopefully this walkthrough gives you a good picture of how how the data and synchronization and triggers work on the USRP RIO getting started projects. So it should give you an idea of, if I were modifying things, I would look at, maybe this block diagram and say, all right, well, maybe I wanted to wait for it to wait on 2 triggers. So, you can kind of look into the logic here and say, okay, well, if I add another trigger here and put an AND gate here, maybe I can make it wait for more triggers. And then same thing, with the data as well. So, hopefully using this information, you should think about, what you'd like to modify in the project, and also think about where in the project you want to modify the functionality, right? Because if you want to modify trigger stuff, you kind of have to be on the FPGA. But if you actually want to modify, like say for example, you want to modify it, instead of sending a tone, you send some, LTE signal or something like that, like a static signal. You can actually do that on the host, right? Um, because all you have to do is, modify where you see that IQ generation happening, right? Um, so yeah, just think about where you want to modify things. So the biggest examples, should we modify things on the host FPGA or both VIs? And so for the LTE example, I would say if you're just playing back something, just modify it on the host, right? But for triggering, you need to do it on the FPGA, right? And you actually might need to modify some stuff on the host as well, so that your other USRPs can get that as well. So yeah. But yeah, hopefully this was helpful, and you can start, your own USRP project and modifying it and making some, really great applications. So thank you for listening, and yeah, good luck on your development.